In this video, we're gonna still find powers, but we're also gonna introduce the concept of energetic balance. So, whenever they're asking you to verify the energetic balance, don't stare at the piece of the empty white piece of paper. It's just basically asking you to make sure that the balance is equal to zero. It's going to be equal to zero. So all the power erogated and consumed are you have to make sure that they are equal to zero. So there is no leak in between for whatever reason. So yeah, let's crack on and have an example about this one as well. So as you can see, this is pretty different compared to either calculus or mathematical methods or other things. This is pretty much, circuits analysis is pretty much about examples. I mean, I could be talking about the energetic balance and so on, but making you, just talk about it, but it's not going to be useful to anyone unless I just crack on and make an example. Because at the end of the day, you're just gonna, solve circuits and find what the problem is asking for. So it doesn't really matter whether I talk about the components and so on or not. You just have to, to be good at what you're doing by solving problems, and that's all matters for your exam. So that's fine. Let's crack on and write. Actually, draw the circuit. So the circuit this time is gonna be well, uh, generator plus E1 minus, then a point which we're gonna call C, then R1, a resistance, then we're gonna have this point here and this point here as well. Those 3 points are going to be connected through resistance. We're going to call this point D. Then we're going to go down here to, I don't know, resistance R3. And then that's it. And then here in the middle, we're going to have a generator of current pointing, I messed up the arrow. Yeah, pointing up, and connected down here. We're going to call this J2. The resistance is going to be our R3. It's going to be our R2. Yeah, and this is R1. Okay, so the problem is saying for the circuit on the left, we know that E1 is equal to 12 volts, J2 is equal to 2 amps, and Ri is equal to I ohm. Find the power actually powers, well the yeah the, well all the power, verify the energetic balance, and the voltage VCD. Okay, as soon as I draw this circuit, there should have been something screaming in your mind, literally screaming in your mind. Whenever I draw, in particular, this area here on the top, because it's pretty clear that this one is just short circuit. Down here, you have a short circuit, and it's never ever gonna go this way, the current, because you know, as it starts and it goes up here, okay, the current has to choose whether to go here, okay, and be connected here and then go back here, or go here and get an additional resistance. It's never gonna go through the resistance, because you know, the current is not stupid. It's not gonna choose the worst path. It's gonna choose the better path. So this one is short circuited and it should not be considered. So I'm just gonna write it. The resistance R, how did I call it? R2. Yeah, R2 is short circuited. Is it a word, short circuited? Well, it just, yeah, this is what I mean anyway. So I mean that this is a short circuit and it's not gonna flow this way, which is why it's kind of short circuited. So anyway, the point is that it's not gonna pass through here. This is a short circuit. So yeah, R2, resistance R2 is kind of short circuited. So I'm gonna consider this circuit. And the circuit I'm gonna consider is this one, which is basically this. And then we have the resistance. And then here we are gonna have the node. And here we're gonna have the other resistance. And everything is gonna be connected down here. And here we have the generator of current connected down here. I should have made this one a little bit bigger. It doesn't matter anyway. E1, R1, J2, R3. Then I'm gonna say, okay, those 2 points, I'm gonna call those A and this one, those A and B. So this one A, this one B. And I'm also gonna say, okay, the current flowing in this direction, from here, I'm gonna call this I1. The current flowing in this other direction, so here, I'm gonna call this I. Now, I can apply the Millmann theorem between the nodes A and B. So if I apply Millmann theorem between the nodes A and B, I'm gonna have VAB, which is gonna be given by, well, just like before in the previous video, E1 over R1 plus J2, everything over 1 over R1 plus 1 over R3. So E1 over R1 plus J2, everything over 1 over R1 plus 1 over R3. So VAB, if we plug numbers into this, well, let me just write them next to the drawing. T was 12 volt, J2 was 2 amperes, Ri equal I ohm, so this is 1 ohm and this is 3 ohms, and yeah, we don't have anything else. It's just a pretty simple circuit. So therefore we have 12 over 1 plus 2, which is 2 amps, over 1 over R1, so 1 over 1, plus 1 over R3, so 1 over 3. Therefore, VAB is going to be equal to, well, just 12 plus 2 over 1 plus 3. So VAB is going to be equal to 14. Oh, well, no, 1 plus 1 over 3. Yeah, I just was almost going to mess up a pretty trivial calculation. So it's 14 over 3 plus 1. Yeah, I was almost going to mess up something very, very stupid. Okay, so basically this is 14 over 3 plus 1 is 4, so 4 over 3. So now if you have a number over a fraction, you can basically say, okay, this is 14 over 4, everything multiplied by 3. So we can say, okay, so VAB is basically 14 over 4, everything's times 3. Which is just, well, this will just be, well, 14 times 3 will be 42 over 4. 42 over 4, I can simplify this. This becomes a 2, this becomes a 21. So VAB will actually be 21 over 2. But I don't like fractions in this case because we're in circuit analysis, so I'm gonna write this as 10.5 volt, of course. Okay, so now I can actually find I, which is this I here, and I'm gonna say, okay, so I is gonna be VAB across AB that we have just found. Sorry about that. Really sorry. Over the resistance. So the resistance we have here, which is R3. So I is 10.5 over R3, which is 3 ohm. So 10.5 over 3 gives us 3.5 amperes. Okay, so now I can finally apply Kirchhoff law, the current Kirchhoff law, to the node A. So I can apply Kirchhoff current law to the node A. Okay, so now I'm just gonna consider the node A, this one here. Okay, I'm gonna draw. Okay. So now I'm considering this node here, and I'm gonna apply Kirchhoff current law. So if you remember Kirchhoff current law, it basically says that you know, there were two, the voltage law and the current law. The current law is basically saying that the sum of all the current entering a node is equal to the sum of those going out from that node. Or we can also say that the sum of all the current meeting at a node is 0. So with that in mind, I can say that I1 is going to be equal to I minus J2. Okay, because we're basically saying, okay, we're gonna consider I getting into the node. Okay, this one, which is I, is going out of the node, and this one, which is J2, is getting into the node. So we have I, which is getting into the node, J2, which is getting into the node, and I, which is going out of the node. This will basically give us, if we consider this, will be, I1 plus J2, okay, will be equal to I. Okay, because we're saying that the sum of the current entering a node is equal to the sum of the current going out from the node, but we only have those two currents going into the node and only this one going out of the node. So those two, I1 plus J2, is going to be equal to I. So I1 plus J2 equal to I. So if we just since we now want to find I because we know those other two, we're basically going to say, okay, I'm going to bring J2 here on the right, so it's going to become negative, and I'm going to have what I just wrote. So I1 is equal to I minus J2. In other words, if we just plug back in this equation, the numbers, we're going to have that I, which we just found, is 3.5. So I1 is equal to I, 3.5, minus J2, which we know and we are aware of because the problem was giving it, was going to, the problem just gave it to us, and is 2 amperes. God, I'm becoming dyslexic something. All of a sudden I can even talk. Why is that? Anyway, so 3.5 minus 2 amps. So I1 is actually 1.5 amps. I mean, it's weird. We're starting to say something trivial, but anyway. So I1 is 1.5 amps. Now, we are getting there because now we have those two currents, okay? And in order to verify the energetic balance, okay, in order to verify the energetic balance, I gotta calculate the power generated, which I'm gonna call PG, and the one absorbed, so the power absorbed, which I'm gonna call PA. Absorbed by what? Well, absorbed by all the elements that are in the circuit. Okay. Once I've done that, I gotta verify that those two are equal. So PG, which is the power generated, is gonna be equal to PA, the power absorbed by all the elements in the circuit. So let's do that. The power generated by the active elements is is basically the one generated by the generator or voltage E1 and the generator of current J2. Those are the only two active elements, because a resistance is passive and this other resistance is passive. An active element is something that is gonna give you more than what it's gonna get. So there is no way a resistance is gonna give you more than what it's gonna get. It's just gonna dissipate the current. So the resistances are passive elements and generators are active elements. So PG, which is the power generated, is going to be given by E1 times I1 plus VAB times J2. So PG is actually going to be given by 12 times 1.5 plus 10.5 times 2. So PG is 18 plus 21, So PG is actually 39 watts. Yeah, the unit of power is watts. Now we expect PA to be equal to 39 watts as well, but we cannot just say, okay, we have found PG, PA is going to be 39 watts, so it's going to be fine. Just 39 watts, that's it. Because, it's actually asking, the whole point is that the problem is asking us to verify it, so to verify that this is true. So now PA, the power absorbed, it is the power absorbed by all the passive elements, so the two resistances in this case, which is the following. It's just R1 times I1 squared plus R2 times I2 squared. I'm sorry, I squared. We didn't call this I2, we call this I. So I squared. Which is going to give me, well, PA equal to 1 times 1.5 squared plus 3 times 3.5 squared. So PA is just 1 times 2.25 plus 3 times 12.25. So PA is, well, 2.25 times 1 is 2.25, and 12.25 times 3 is 36.75. So PA, as we can see, is also 39 watts. So just like I expected, PG is equal to PA, which is equal to 39 watts. So we have just verified the energetic balance. The power generated is going to be equal to the power is, well, it's not going to be, it is equal to the power absorbed, which is 39 watts. Now, there's only one thing left that the problem was asking us, was to basically find the voltage VCD. So the voltage VCD is pretty trivial. VCD just VR1. So VR1 is basically R1 times I1. Because it's at these, well, no, it's CD, so it was basically at this end, at these two ends, but it's not going to be there, so it's just R1 times I1, so it's the same of this current here. So VCD, I can just say that it's as simple as 1 times 1.5, so VCD is actually 1.5 volts. So that's it. This is how to verify the energetic balance. Remember, you gotta find the power generated by the active elements, generally generators, and verify that it's equal to the power absorbed by the passive elements, in this case, the two resistances. So once you verify that they are equal, that's problem solved. That's absolutely fine.